memberikan penghargaan kepada karyawan melalui kesejahteraan yang baik, penyediaan lingkungan kerja yang aman dan nyaman, serta kesempatan untuk mengembangkan karir. Produk-produk PT Multibangun Rekatama Patria. Produk Tensar System terdiri dari Geogrid Tri-X, terbuat dari bahan polipropilin berkualitas yang berfungsi sebagai stabilitas tanah dasar, khususnya pada tanah lunak. Multi-block retaining wall system. Multi-block retaining wall system merupakan sistem konstruksi dinding penahan tanah segmental, perpaduan antara modular blok beton sebagai facing dan tensar uniaxial geogrid sebagai perkuatan tanah. Geomembran. Geomembran terbuat dari polimer plastik yang bersifat kedap terhadap cairan. Kami juga menyediakan produk-produk geosintetik lainnya seperti geotekstil, material drainase, serta geosintetik clay liner yang menjadi solusi bagi proyek-proyek Anda. Gudang PT Multibangun Rekatama Patria hanya 5 menit dari gerbang tol Bitung Tangerang, sehingga memudahkan akses pengiriman material. Gudang PT Multibangun Rekatama Patria terletak di kawasan pergudangan pengembangan kawasan terpadu 2, Bitung Tangerang. Yang mempunyai luas 3.300 meter persegi yang dapat menampung material geosintetik dengan pengaturan dan penyusunan material yang tertata rapi. Serta pengoperasian alat dengan tenaga profesional. Hingga sampai di lokasi proyek. Selalu ready stock dan pelayanan profesional adalah komitmen kami. Dengan pengalaman dan pelayanan yang teruji, maka jangan ragu untuk menghubungi kami. Kunjungi website kami di www.multibangunpatria.com.
Ladies and gentlemen, it is a pleasure to welcome you back to MRP webinar series in 2023 under the theme Application of Fundamental Geotechnical Testing and FEA in the Development of Design Methods for Unpaved Roads and Platforms. This event is brought to you by PT Multibangun Rekatama Patria, Geosynthetic Specialist. My name is Rifa and I will be serving as your master ceremony in this event. Before we start, allow me to read the rundown of our event this afternoon. First, I will be reading the rules of the webinar. Second, there will be opening remarks by the representative of PT MRP, Bapak Insinyur Antonius Bagus Wijaya. After that, the event will be continued with the introductory presentation by Bapak Michael Dobie, and he will continue as our moderator to start the presentation of our main speaker, Dr. Andrew Lee of Tensar. The event will then continue with a Q&A session. We would like to ask you to stay with us until the end of the event because, like usual, we will be doing a quiz with a total of 750,000 for 3 winners. We will also give you access to the e-certificate at the end of this webinar. Ladies and gentlemen, for your own convenience, please put attention to the following rules. You can submit your questions for the speaker to the Q&A feature located at the bottom of the screen. The question should be in English. You can raise your questions before, during, and after the presentation of the speakers. We expect you to stay with us until the end of the event to get the information you need regarding the e-certificate and also the soft copy of the presentation from the speakers. This event is also live streamed on our YouTube channel, Multibangun Rekatama Patria. If you have any technical questions, please contact us by scanning the QR code shown on your screen or visit the link linktr.ee/MRP webinar. The link is also there in the chat box. Now, without further ado, I would like to invite the representative of Multibangun Rekatama Patria, Insinyur Antonius Bagus Wijaya, to give his opening remarks. To Bapak Bagus, the time is yours.
Good afternoon, ladies and gentlemen. I would like to welcome all of you to this webinar. Thank you for taking your time for being here with us today. First, we would like to thank to the God Almighty for all the blessings and gifts to attend to this great event. I am also very thankful to Mr. Mike Dobie and Mr. Andrew Lees for presenting here with us today. I also wish to thank all of the committees who have organized this webinar. Let me introduce myself, Bagus Wijaya, representing PT Multibangun Rekatama Patria, a company with a lot of experiences in geosynthetic specialist field since 1991. We are fully committed to develop quality products and also actively for participating in national development according to our fields, such as geogrid materials for road infrastructure, subsoil reinforcement, port access routes, container terminal construction, embankment reinforcement, and landslide handling. There is also geomembrane material for ponds to contain wastewater or to conserve clean water, and also for landfill. We are regularly share experiences related to geosynthetics and also geotechnical fields through webinar and workshop. We share this webinar as our contribution for civil engineering in general and the geotechnical field in particular. Hopefully, it can provide positive benefits and advantages for all of us. Welcome to the webinar. Thank you.
Thank you, Bapak Bagus, for your kind remarks. Ladies and gentlemen, before I give the floor to Michael Dobie and Andrew Lees, I would like to read the short profiles of our two distinguished speakers today. Starting from Michael Dobie of Tensar International. Bapak Michael Dobie is a highly accomplished geotechnical engineer with over 40 years of experience. He holds a BSc in Civil Engineering from Bristol University and an MSc in Soil Mechanics from Imperial College London. As a Chartered Engineer and Fellow of the Institution of Civil Engineers and the Chartered Institution of Highways and Transportation, Michael Dobie has significantly contributed to projects worldwide encompassing highways industry, buildings, transit systems, bridges, and quays. He is an active member of the Institution of Civil Engineers and the International Geosynthetic Society. Later, we will have Dr. Andrew Lees to give his presentation. Dr. Andrew Lees has extensive experience of putting the application of geotechnical research into practice. Andrew Lees gained his PhD in geotechnical engineering from the University of Southampton, then worked in consulting for 4 years. Then, as assistant professor of geotechnical engineering at Frederick University, Cyprus for 12 years. He is also the founder of the consultancy GeoFem, which specializes in geotechnical numerical analysis. Andrew now undertakes research and development for Tensar and is the originator of the P-value methodology for working platforms and now a new design methodology, LAAMS. Now, before I give the floor to Bapak Michael Dobie, I would like to remind you that you can start submitting your questions from now, during and after the presentation by using the Q&A feature. We would also like to remind you to stay with us until the end of the event to get the information you need regarding the e-certificates and also the soft copy of the presentation from the speakers. Now, please welcome Bapak Michael Dobie. To Bapak Michael Dobie, the time is yours.
Thank you very much, Rifa, for your very nice introduction, and also to Bagus for his introduction as well. Before I start, I'd like to thank everybody who's joined our event today. It's very nice to have people participating in these events and have a chance to share information about various geosynthetic topics. But today is I think it's a rather interesting and special one. I think I need to share my screen, and then I need to start showing you a few slides. So here we go. Good. I think everybody should be able to see this now, and I hope you can all hear me. The topic today is unpaved roads and working platforms. These sound like they're quite similar, but of course, in terms of the way we design them and the way we regard them, there are quite big differences as well. So the question of design is an important one, and you've already heard from Rifa just then that my colleague Andrew Lees has been involved in developing new design methods, but I thought it would be a good idea just to introduce these particular forms of structure because they are quite special. So let's just have a look at a few unpaved roads. I think we all know what they are. They are roads built generally from gravels or aggregate materials, and they are normally supporting trucks. Of course, they can support other loads as well. They can be built for a variety of subgrade conditions and also a variety of vehicle loads, from large trucks down to very small ones. And also a variety of axle loads. Here is a very long vehicle, so it has many axles, and the contribution of all the axles must be taken into account. And quite a common problem here we have in Indonesia, of course, is overloaded trucks. I think there's one that is hugely overloaded with a lot of tree trunks on the back of it. So something else we need to think about in our designs. Then working platforms, these are generally being designed to support various loads on a construction site. They're often considered to be temporary structures, but sometimes they do have to provide a function for much longer than that. And of course, they can be designed for a variety of subgrade conditions and also a variety of plant loads. You can see there an image where we have some piling rigs on a working platform in Germany. And here we have another picture of a particularly huge crane that's being supported also on a working platform. And this one, you can see how big the tracks are, but this is applying a pressure of 500 kilopascals maximum. So an absolutely massive load. So to help provide information about both of these forms of design, Multibangun organized 2 design workshops. This one about 3 months ago was for the design of unpaved roads. And then just 2 days ago, we had another workshop looking at the design of working platforms. And what I promised during both of these events was that the design methods, which I described in a brief way, I was very keen that I should get my colleague Andrew Lees to spend some time in a webinar. Sadly, he can't come all the way from Cyprus today to do this, so it's a webinar. But ask Andrew to explain the background to the design methods that we were using. But I thought before I actually ask Andrew to talk, I'd just like to make a few little points about some aspects of designing both forms of structure. And first of all, I mean, what are we trying to achieve? Well, when it comes to an unpaved road, the load is going to come from a wheel and a certain number of passes of that wheel. There'll be a subgrade of some sort, an aggregate layer, and our target is to find out what the thickness of the layer is. Therefore, we need this minimum thickness to provide the required design life. Now, when it comes to working platforms, it's very similar. We have a loading. In this case, the way it's shown there is from the track of a crane. Likewise, again, subgrade properties and aggregate properties. And we want to know what is the thickness. But the targets are a bit different when it comes to working platforms. In fact, the number one target is safety. We need to make sure that these bits of equipment don't fall over. Sadly, there are many reports of this happening that you'll see from time to time, but a well-designed working platform is vital. And therefore, our target then is to find minimum thickness, but it still must provide an adequate factor of safety when we design it. So if we just think about those two main applications, then for any particular subgrade, we might need to design some form of access road for trucks, and that would have generally a target given by a rut depth, a target rut depth to be achieved. And then that might lead onto a working platform where we have a heavy crane, and generally the target or performance target there would be to achieve a certain minimum safety factor. And these are things that are all part of the input into the design methods. Now, during our workshops, we provided the participants with some examples which they actually designed for themselves using our new software platform called Tensar Plus, which I'll show you briefly in a second. But you can see from the images there, which are actually the same as the previous ones, in the first one, 3 months ago, we designed an unpaved road, and in the second one, just 2 days ago, we designed a working platform for a crane. But I don't know if you can just about read it. Here are the design methods. This one is called the Lees-Hahn method, also referred to as LARMS. Now, I'm probably going to ask Andrew to explain further on that terminology. And then the platform was designed using the t-value method. And these are the two methods I'm very keen to let you hear more about when Andrew talks shortly. But before getting there, I thought I'd just tell you a couple more things about design of these structures. Before I get there altogether, here is the view of the Tensar Plus platform. This is newly developed software, which is cloud-based, and there are a growing number of design methods, which you can see on the left-hand side, and also features of the design methods. This is constantly under development. But if we look at the road design side of it, the first one in the list there, then we can see a number of methods there, and the one that we're interested in is the unpaved road method. That's the one that Andrew has developed over the last few years. And then there is a view of the program. That is what it's looked like. So anybody who came to our workshop or either of the workshops would have had a chance to use this, which they can simply do by registering to get access to the software. So that was the unpaved road design. And then we switched to platform and the working platform method. And this is what we were doing just 2 days ago. And there is a typical working platform design. So, in reality, design methods for both unpaved roads and working platforms have been available for many years. And in fact, many of them were highly empirical. When we say that, we mean that people build roads, observe the behavior, and by doing that, they can develop sufficient information to actually create a design method. So this is what we call an empirical method. And likewise, the addition of the benefits of geogrids was also carried out empirically. So what I thought I would do is just to have a look at the design method for unpaved roads. Now, this is one from a long time ago, so I think it'll be explained quite nicely in the next slide. Here we are. So this was published in 1981, so that's 42 years ago. And it was published by Giraud and Noiret. Of course, J.P. Giraud is a very well-known name in the field of geosynthetics. And this is a purely empirical method. And I thought I would just show to you in a simple way just how empirical it is. So what we're trying to do is to design that granular layer. We want to find out the thickness H. And when it says little s, that's for stabilized with geogrid. And so the input would be the number of passes of what we call a standard axle, which has a weight of 80 kilonewtons. That's N75. And you might say, well, what's the 75? Well, the 75 is the target rut depth that we're going to design for 75 millimeters. So the subgrade is then represented by its CBR value in this particular design method. And then the granular material would be assumed to be of what we would normally call a sub-base quality. So that's the various input parameters. So having established those input parameters, we then simply go to this little equation, which gives us the thickness of the layer. And if you look in the equation, you can see N75, and you can see the CBR to the power of 0.63, and also FSN, which is a factor to take into account the stabilization effect of geogrid. And that gives us the thickness. And when we see various numbers in it, like 190 and 0.63, those are constants which were derived when the method was created in an empirical way, so that they could fit the method to observe behavior. I thought we'd do that. So I thought we would look at a particular piece of testing carried out in the UK a few years ago by the TRL. That's a Transport Research Laboratory in the south of England. And this was testing done by a machine that you can see there, the yellow machine, which basically runs a wheel up and down over a trial pavement. And in this particular case, the pavements had a thickness of 300 millimeters of granular material of a sub-base quality, and the supporting subgrade was a soft clay. It had a CBR of 2%, it was actually a fairly highly plastic clay. And then the applied load was a 40 kilonewton load, because it's one end of a standard axle. So it's not the 80 kilonewtons, it's 40 kilonewtons. And that's the same as one standard axle every time it goes. So it goes up and down like that. And then our interest is to measure the developing rut depth, we see there where wheels are running. And having completed any particular set of testing, we will then get a trafficking result. We'll look at it in a minute. But my target here was to see how does that compare to the prediction from the Giro-Noire design method. So let's have a look. So here is a particular result of a trafficking trial test carried out by TRL. We have in the horizontal direction on the axis is in standard axles, ESALs, and it's logarithmic. It's sometimes easier to look at this data in a logarithmic scale, so logarithmic. And you can see the numbers going there up to 100,000. So that particular, there are two results there. Unfortunately, I'm afraid the slide has slightly changed its the dimension of the ledge in there. But the blue line is the stabilized case, and the green line is the non-stabilized case. So therefore, we call that a control where we don't have any geogrid. So that is what a typical trafficking result looks like, comparing a stabilized section to a control section. So having got that information, I then went to the Giro-Noire method, and I calculated the number of standard axles required to achieve or to get for a 300 millimeter pavement. That's the thickness that was used in the trials. And if you do that, they look like this. So we have the 300 millimeter, the red color is the control, and the black color would be the stabilized pavement according to their method. And you can see that the prediction, according to that formula we saw just now, is quite a lot below the actual performance. Now that's probably a good thing, because these methods are very empirical, and they rely on a relatively small number of parameters in the input. Then being slightly conservative is probably a good thing. But just how conservative are they? Well, what you can do, having got to this stage of the calculation, you can then, in the Giro-Noire method, adjust the thickness of the pavement until it meets the actual trafficking performance. So let's just do that. So that's just talking about the significant under prediction. And we have these results. So to move the result using Giro-Noire over to meet up with the actual trafficking behavior, we need 354 millimeters in the case of the control, and we need 388 millimeters in the case of the stabilized pavement. So you can see that we are, if you like, we have a fairly conservative result, and we could make those pavements quite a lot thinner in reality compared to what comes out of the design method. So it's a very nice indication of the relative conservatism that we see in this kind of method of design. And then just quickly, I'd like to look also at the same thing for working platforms. So working platforms have generally been designed in the past using a load spread method. So let's just see what I mean by a load spread method. So back to this same kind of cross section where we have the granular material in the light color and the rest is the subgrade. And we apply some kind of load from a crane track maybe. And the load is in kilonewtons, of course, at this stage. So we can then, what we normally do with that load, we spread it. Oh, sorry, just so the other parameters, we have again, an undrained shear strength, in this case for the subgrade. And we have a target safety factor. So the parameters involved are quite small number of parameters. And we then look at the design by using, in this case, I've used a 45-degree load spread, which is very common in the case of stabilized layers. And having done that, we calculate the pressure on the base, taking into account that load spread. And then we can also calculate the bearing resistance of the clay, just by using a bearing capacity approach. And then what we do, we find a safety factor by simply dividing the bearing resistance by the applied pressure. And of course, we want that to be above a certain target, maybe 2 or whatever it might be. So that would be the load spread approach. So let's have a look at a quick example of this. This is in Thailand. And what was going on here was that this particular site had a lot of dredged fill. That's the gray colored material in the middle of the picture, which is very, very soft indeed. It had been dredged from the sea beside the, this is that blue color at the top is the sea. So dredging had been used to maintain the depth in front of this area and had been placed in a hole in the ground. But they then wanted to use this area as a working platform, and the soil was incredibly soft. So they decided to carry out a trial of an MSL, and the way they built it was like this. They started off with a sand layer, and that's where they placed 2 layers of geogrid, and they then finished it off with an aggregate layer, which is the slightly grayer color material you can see there. And having built the working platform, they then loaded it with concrete slabs. And these particular slabs weigh 5 tons each. And they have an area of 2 meters by 2 meters. So if we look at a cross section, it looks like this. So drawn approximately to scale, and we can see the thickness of the platform there. Total thickness is 1.5 meters. It's quite significant. And we can also see that first 5-ton slab being placed as a loading. So having done that, they then start to place more concrete slabs. Now these big ones, they weigh 20 tons each, and they're placed on top of the smaller ones, and they place a few more. Now, at this stage, what you might notice with 4 slabs there is that we start to see a crack around the edge of the working platform area. That's as far as the geogrid extended. So you can see quite well a significantly wide platform developing as the load is applied. And here is a view of the final arrangement where we have 5 of these slabs, and there's a close-up view. And you can see very clearly there at the back of the platform, this crack that's formed at the edge. So how would we analyze that? So if we go to the full cross-section, it looks like this. So we have all of the concrete slabs, which weigh in total 115 tons with a base area of 4 square meters. So we can very easily calculate a pressure, which is 290 kilopascals, which is very high. Now, if we go down to the soft clay underneath, although we didn't have particularly good data, based on the information that we had, we estimated based on an undrained shear strength of about 7 kilopascals, that the bearing capacity would be 43. Now, clearly it hasn't failed, so let's try analyzing this with a load spread approach. So we'll use a 45-degree load spread. And if we do that, then we find that, quite interestingly, the applied pressure through that load spread is also predicted to be 43 kilopascals. So you might say, well, that's good. The bearing capacity is sufficient to support the load. But of course, if they're equal, that's going to imply a safety factor of 1. And we definitely don't want a safety factor of 1 with a working platform. So we can see that that approach has not worked very well. We want a safety factor of significantly above 1. So we can see here that the working platform has provided far better performance than would be predicted using a 45-degree load spread. So I think I'm coming to the end of this little introduction, but so there's a question here: can we improve on these design methods? Now, again, what Andrew has done, he's taken up this question very seriously and decided that we definitely can. And so Andrew has worked away. I think Andrew he's been a colleague of mine for almost 10 years, I think now. He can confirm that in a minute. But he set about trying to improve the situation with these design methods. And he did it starting off with some very fundamental research. And then he used his very extensive experience of finite element analysis to help with the developments as well. And then he put this together to create methods for designing both working platforms and unpaved roads. And I'm not going to say any more about it because Andrew's going to tell you all about it very shortly. But it has been a really extraordinary development. And these methods are the ones available in Tensar Plus that we saw just now at the top of those 2 worked examples. And before I hand over to Andrew, I would just like to remind you that that these design methods are based on the assumption that we have an aggregate and geogrid composite. The 2 materials work together to create what we call a mechanically stabilized layer. And this is how it works. I'm sure Andrew is going to mention this again in a minute. I'm sure he will. But this is a very important starting point for this kind of approach to unpaved roads and working platform and the design methods that we use. So you've already had a very nice introduction to Andrew's background from RIFA. Thank you for that, RIFA. And I also mentioned he's been a colleague for quite some time now. He's added a lot of expertise to what Tensar has been doing in terms of development and analysis of many forms of engineering structure, not just platforms and roads, but I just now need to make the last couple of comments and basically to hand over to Andrew. Andrew, I'm looking forward very much to your presentation. And so I'll bring my little introductory session to an end now and ask you to take over.
Well, thank you very much, Mike, for that very informative and useful for me introduction. Yes, it is nearly 10 years that we've been working together on these things. So let me continue then. And well, firstly, by thanking everyone for attending this webinar. I hope you find it interesting. We're going to get into some detail now about how we have derived these new design methods using mechanical stabilization. So I'm going to start off by describing a bit about what is applied mechanical stabilization. And that is where the acronym LAMS comes from, LAAMS. The LA is the Lees approach, which wasn't my idea, but that's what Tensar wanted to call it. And AMS is applied mechanical stabilization. So mechanical stabilization by Tensar geogrids is something that you will have heard us talk about for many years. But we have developed a method to characterize that, to put numbers to that. And that has allowed us to apply mechanical stabilization in a numerical form to new design methods. So that is the umbrella term for these new design methods. They are called LARMS design methods, and that includes the t-value method for platforms, which is to avoid situations as shown in the photo on the left, a complete failure of a platform. Maybe that isn't even a platform at all. That's just the subgrade. And as Mike mentioned, that is a safety critical design. We need to have factors of safety to avoid having accidents. And we've also developed a LARMS method for unpaved roads. And that is to avoid situations that you that you see on the right, not safety critical, but serviceability critical. We don't want trucks getting stuck in roads like that. Now, on a similar theme to what Mike was presenting, just a few more words on why design methods change. Why don't we just stick with the old methods? Well, the early methods were empirical, as Mike said, and he demonstrated very well the drawbacks of a simple empirical design method. It works very well for the situation that was observed. So some sort of field test was performed, and the design method was created to match with those performance conditions. But as you move away from those conditions, then the methods become inaccurate. So the way the industry is now, we have a greater need for precision. We need to be as efficient as possible with our designs. So these empirical methods, they can become uneconomical. So as Mike showed in the unpaved roads case with Giroux-Nuret, when compared with the TRL testing, it was rather conservative. So if we continue to use that design method, then all our designs would be more expensive than they need to be. Worse still, in some situations, they could become unreliable. So they will give aggregate thicknesses that are too thin, and we may have serviceability problems with unpaved roads, and worse still with platforms, we may have a risk of failure of a crane or a piling rig. So it's all about trying to get better precision and better accuracy with our design methods. Now, if we only have the empirical methods, what inevitably happens, because there's no other method available, is they start to get used in situations for which they are not applicable. When these design methods are published, there's normally a lot of limitations that are added to the method, saying it should only be applied in these cases. But often that gets ignored. People need to produce a design. There isn't anything else available, so they will continue to use these methods for situations where they were not intended. Now, the risk of doing that, well, it's a bit like tightrope walking, as we see this monkey here. If you know what you're doing and you're very experienced at doing these designs, then maybe you'll get away with it. You'll be able to use these design methods and you'll understand the limitations and you can make adjustments. But if you are fairly new to these design methods, using these basic empirical methods, you could very easily get into trouble. And because these new design methods are going into our Tensar Plus design app for everybody to use, often for them to use without consulting with Tensar, we do not want to give people design methods that will get them into trouble. We need to give them design methods that are robust and they are going to work in a wide range of cases. So that was our main motivation for producing these more accurate, more reliable design methods. So as promised, a little bit about applied mechanical stabilization. So you see that, that block of material there called an MSL. That's what we call a mechanically stabilized layer. So it is aggregate with stabilizing geogrid within it that improves the properties of that aggregate. So rather than geogrid reinforcement with a certain tensile strength plus an aggregate, we consider them as one composite material. And we have been using the term MSL for many years, well over 10 years. But for a long time, it was a concept. We knew it existed, and we had done tests to show that there is a mechanical stabilization function, but we had no way of measuring it. So if anybody asked the question, how strong is it, or what are the mechanical properties of this material, we were not able to answer the question. That is until recently. What we have developed is a method to measure the mechanical properties of a mechanically stabilized layer. So we have built these very large triaxial rigs. So anybody that has studied soil mechanics as part of a civil engineering degree will be familiar with the triaxial test. In the university laboratory class, it will typically be about 76 millimeters high, the specimen, and 38 millimeters diameter. This is the same test, but it's much bigger scale because the aggregates that we are testing can be quite large. So you need to have a sufficient diameter so that you don't have particle size effects. And also when we put in the geogrid, we need to have a sufficient number of apertures to have a representative behavior. So we have a specimen 0.5 meter diameter and 1 meter high. So big that you can actually hide behind it, as I'm demonstrating there. So the aggregate is inside there, and here's the rubber membrane, just like a standard triaxial test, but there is no cell to go around it because it's just too big. So we apply the confining stress by applying a vacuum to the specimen. So you can see that the rubber membrane is being pushed into the aggregate by atmospheric pressure. So we perform tests on the aggregate without geogrid at different confining stresses, and then we test the aggregate with a specific geogrid product, usually just one layer placed at mid-height, but sometimes more layers to get the mechanical properties of the composite. So we measure what the geogrid does to the aggregate rather than just measuring the geogrid properties in air on their own. So this was the first rig that was built. On the right is the second rig. I've just started the video that it's a speeded up video showing you the test in progress. So it's just a compression test in the usual way, and we push it until we get a shear failure within the specimen. And these bands around the specimen also measure the radial strain in the specimen. When we get the test results, that allows us to characterize mechanical stabilization using this constitutive model, or a constitutive model called the Tensar stabilized soil model that incorporates this failure envelope. So it's characterized in terms of principal stress space, but the shapes here of the failure envelopes would be similar in more stress space that is more typically used. So we have a slope here, which is due to the frictional strength in the aggregate. It has a slope K naught. That could be related to the friction angle, phi, directly. The reason it's not phi is because we're in principal stress space. But we have this frictional component of strength in the aggregate. Now, when you test a compacted aggregate, you will notice that you will get an apparent cohesion due to interlock between the particles and dilatancy. In reality, it's a curved failure envelope. Because there's no real cohesion, the failure envelope curves down to the origin here. So this black failure line could be used to represent the aggregate on its own without GeoGrid. But when we add a layer of GeoGrid in the middle of the specimen here, we see that the properties of the aggregate are improved around here. And we see a higher failure envelope represented by the red line. And you see it gets to a higher apparent cohesion, which makes the line highly nonlinear because it needs to pass through the origin. So we get a very curved failure envelope. And this is caused by all the extra interlock between the particles and the GeoGrid. So the area between these failure envelopes represents the additional shear strength brought by mechanical stabilization. So the red line represents the strength of the aggregate here where the GeoGrid is located. And as you move away from this plane here, the strength will gradually decrease until you get to the strength of the non-stabilized aggregate represented by the black line. So when we implement this into a finite element analysis software, the failure surface varies with distance from the GeoGrid. It varies between these two lines. So you see how we needed to develop our own constitutive model to incorporate these features, the nonlinear failure envelope and the variation with height from the GeoGrid. Now, when we developed that revolutionized our understanding of all applications with mechanical stabilization, as you shall see. So we've been able to use it in specific projects, such as this example shown up here of a crane platform. But it's also helped us to develop new design methods. So that triaxial testing and the constitutive model are all described in this peer-reviewed journal paper in the Canadian Geotechnical Journal. So if you need more information, you simply need to obtain a copy of that paper. So that's the background to applied mechanical stabilization. Let's see now how we are applying that to the two design methods that we are going to cover today. One for working platforms, which I'm going to do now, and the next one for unpaved roads. The reason I'm doing the platforms first is because you will see in unpaved roads that we are using the platform design method. So it's logical to cover the platform design first. So to develop what we call the t-value design method, we looked back at existing literature in this field, and we found these centrifuge model tests performed on circular and strip footings on an aggregate layer, actually sand in this case, overlying a clay subgrade. So in the model test, they did different H values, so different thicknesses of the granular layer and different widths of the loading and different strengths of the subgrades. There were no geogrids in these tests, so we were just deriving a completely new design method without geogrid that would allow us later to incorporate the benefits of stabilizing geogrid. So these results from model tests show the bearing capacity, QU, that was obtained, and we have normalized it by QS which is the surface bearing capacity of the subgrade. So if there was no granular layer and the foundation was on top of the subgrade, then QU would be the same as QS. Hence, when H equals 0, the ratio is 1. But as H increases, you see we get an increase in the bearing capacity ratio because of the higher strength of the granular layer. And for the strip footings, they seem to lie on a straight line. And what we found was the slope of the line changed depending on the strengths of the granular layer and the subgrade down here. So we called that slope the T value, or the load transfer efficiency of the granular layer. So that's where the name of the method comes from, the T value method. So this is the equation of the line that you see here. So this ratio is equal to 1 because it starts at 1 plus the slope T times the ratio H over B. And we found that with square or circular footings, we also got a straight line relationship if we squared the term in the brackets here. So with that new simple way of characterizing how efficient this granular layer is at improving the bearing capacity, we were able to derive a simple to use design method. And then when we add mechanical stabilization, because it increases the strength of the granular layer, it will increase the T value. So we looked back in the literature at various numerical analysis studies. So here's an example of where we can use finite element analysis to derive a routine design method so that you do not need to do finite element analysis for every design. So these studies were already published. So the FEA studies were from the University of Oxford, where they did a number of FEA models, where the number here represents the friction angle of the granular layer, so 32 degrees, 40 degrees, and 48 degrees, on clay layers of different strength. And the FELA is finite element limit analysis, performed by Professor Scott Sloan at the University of Newcastle in Australia. And again, the numbers represent the friction angles 30, 40, and 50 degrees. I've also added the centrifuge testing here with an embedment depth of 0. If we take the two cases with 40 degrees, the green and the orange dots, you see they lie together. So there's good agreement between the two approaches. And we were able to draw lines through these. So you see here with a granular layer friction angle of 40 degrees, this is how the T value varies. And you see how it increases as the subgrade gets weaker. And the subgrade strength is normalized by the effective overburden pressure on the subgrade. So it becomes dimensionless. That's another big advantage. It makes the method applicable across a wider range of cases. So the T value increases with the strength of the granular layer and increases as the ratio of the strength of the two layers increases. So we derived that for the strip footings, and we also looked at numerical studies with circular footings, and we found that the same 4 lines that we have here provided a lower bound to the circular footing. So we can use the same lines for circular and strip footings, which means we could use the same lines for all rectangular footings with B over L ratios in between. So that method was peer-reviewed and published in the ICE proceedings. So again, if you want to read more information about that design method, then you just need to obtain a copy of that paper. Now, how do we introduce the benefit of mechanical stabilization? That's really why we develop these new design methods, is to show more accurately the benefit of mechanical stabilization. So here we have the same curve that we saw just now. For a phi value of 45 degrees, this is how the T value depends on the undrained shear strength SU of the subgrade. Here is a curve that we had derived a few years ago for our Triax product with crushed rock aggregate. But now we have a new product, Tensar Interax. It's higher performing. We need to derive a new curve. How do we do that? Well, we do the triaxial testing that you saw. We derive the input parameters to the Tensar stabilized saw model with the curved failure envelope. We take those parameters and run a parametric study in FEA with lots of different platforms, with different thicknesses of aggregate, different widths of loading, and different strengths of subgrade for both plane strain and axisymmetric conditions. We calculate the bearing capacity for all those cases, and we back calculate the T value. So we get a number of points like this from the FEA parametric study. So again, this is how we're using FEA to develop new design methods and also to obtain the parameters for the new design methods. So we draw a line through here, a cautious estimate of the average through there, and there we have our T values for the crushed rock aggregate with Tensar Interax, and you see the superior performance. Again, it's all peer-reviewed and published. You can obtain this paper. All these papers I've mentioned, they're available on my ResearchGate profile, so you can obtain them through there. This one's publicly available, so you can get it right away from there. Now, this is all theory I've shown so far. Should you just believe me and take my word for it that we've got the right numbers from the triaxial test and our FEA parametric studies are correct? Well, you shouldn't just take our word for it. You should need to see some full-scale validation. So we've done lots of this. Here's an example from the University of Saskatchewan in Canada. They have a dedicated test site with a soft clay subgrade. So they excavate this trench to get down to the subgrade, and they construct a platform all the way along this trench, and they perform plate load test after plate load test on this platform using this bridge here and the trucks to provide the reaction force. So there's a close-up of a 1 meter square plate that's being pushed into the working platform here. There's an example of the aggregate that's been used. So we've tested a range of different aggregates, from high quality crushed rock to this lower quality crushed river gravel and other materials. Tensar ground coffee. There's just a plug for the vlog that I run. You can find that on the Tensar website and on YouTube. So one episode of that comes from the test site here, so you can find out a bit more about the site. Now, here's a speeded up video of one of the tests. So you can see what full-scale validation of a bearing capacity method looks like. It's a 1 meter square plate because track widths on piling rigs and cranes are typically around about a meter wide. But nobody else has done this sort of testing because it's very difficult. A 1 meter square plate requires a very big load to push it all the way to failure. And you can see this bridge being pushed up during the test because of the load that's generated. So this is 40 tons that's being applied here to make it fail, but we've got a clear failure plateau here. So that was the background to the platform design method. Now let's look at the unpaved roads design method. Once again, the aim, the efficient construction of unpaved roads. So let's make this thickness H only as big as it needs to be, but no bigger, just so that we use less aggregate and save money. It's got the slightly ironic title, this slide. It's simple, isn't it? Well, the aim, or the objective rather, of the test method is simple. We're just trying to calculate this H value to allow a certain axle load to pass n number of times over a subgrade of a certain CBR. So that's pretty simple, but we'll see that the detail of the calculation gets quite complicated. So we've developed an entirely new design method, and it's all new right from the start when we look at the tire contact area. Now, older methods such as Giroux-Nuret that Mike showed earlier, they don't even consider the tire contact area. It is simply an axle load. So it doesn't matter. It doesn't take into account the size of the tire. So a big tire will apply a much lower stress than a small tire. So the Giroux-Hahn design method did take that into account by assuming a circular contact area and that the applied stress equals the tire inflation pressure. But we thought, now, is that really the case? Is it circular? And the tire inflation pressure on modern trucks can be much higher than the bearing capacity of the unbound aggregate. So how could it possibly be equal to the tire inflation pressure? So we did some investigation. At the US Army Corps of Engineers test facility, we used the loading truck they have here with a dual tire, similar to the TRL facility, but this one is actually driven by a truck. And they can change the weights here as well as changing the inflation pressure. So we did some experiments with 2 different wheel loads and 2 different inflation pressures, and put some brown paper on a thin rubber sheet on the unbound aggregate. And we drove the wheel onto the brown paper, sprayed paint around the base, and measured the contact area. What we found is that the contact area is rectangular, not circular. The contact width equals the tire width. It's the length that varies. But actually, it depended more on the tire load than it did on the inflation pressure. So let's look at the measured contact area here. Or over here, it's the load divided by the area to obtain the average contact stress. For all the different cases we looked at with the different tire inflation pressures and the different wheel loads. And we even did some experiments on concrete as well to see what a rigid surface would look like. But look at the average contact stress. So the tire inflation pressure was 827 kilopascals. The contact stress was only 400. So less than 50% of the tire inflation pressure. So the existing design methods such as Giroux-Hahn are completely wrong with the tire contact stress. So right at the beginning of the calculation, they're already 50% out. So as we thought, because of the compressibility and the and some yield in the unbound aggregate, actually the contact area, it gets bigger and the contact stress reduces. So the traditional method of predicting contact area by the tire inflation pressure, you see how it can underestimate the contact area or overestimate the contact stress by a significant amount, although it works reasonably well on a rigid surface. It's just not on an unbound aggregate. We developed a new method based on Hertzian contact theory. So it's the contact between two objects, dependent on the stiffness of the two objects. And by doing that, you see we got a much more accurate method of predicting the contact stress. So that is implemented into the new unpaved roads design method. And the big advantage of doing that is that if you get the fundamentals right, then you can apply the method across a wide range of cases. So the complete opposite to the empirical methods that suit only the particular test conditions that were studied. If you get the fundamentals right, you can then apply this on a wide range of tire sizes, right from the heavy haul mining truck to a small pickup truck. And we can even consider explicitly the difference between single tires and dual tires, as you see here. And we can consider a wide range of axle loads. So this one new design method is used both for heavy haul mining roads, but also for more lightly loaded or road-going trucks on unpaved roads. But that introduces some new input parameters. So the tire width is needed. That's on the side of all tires. You also need the radius as well. Now, you may not always have that information, so Tensar Plus helps you out, gives you some typical values. But if you do know these values, you can input them into the design. So this new way of calculating the tire contact area was recently published at the Canadian Geotechnical Conference just a couple of months ago. So that is available to get more information about that method of calculating tire contact area. Again, that's on my ResearchGate profile. Now, the main purpose of the design method is to predict rut depth. That is normally how performance is specified. Here's a video showing you what excessive rut depth looks like. Clearly, we don't want this situation on our roads. It gets much more difficult for trucks to use the road. The road deteriorates more. And in this case, you can see how it fills with water, and that just creates even faster degradation of the road. Now, our method has a completely new way of calculating the permanent rut. It does it in two stages. It calculates a theoretical rut on the first pass, and then it adds the accumulation of rutting on subsequent passes. Now, you'll see why that is shortly. So on the first pass, you apply a wheel load and release, and you are left with a small permanent wheel path settlement, SP, at n equals 1. That is made up of a subgrade permanent settlement, ST, and perhaps some deformation of the base layer, the aggregate, subbase permanent compression, SG. These are all theoretical values. This is not something you would try to measure in practice, just one truck and then measure it, but you'll see how the calculation works in this way. Now, a new feature is we're calculating separately the subgrade settlement and the aggregate deformation. One good reason to do that is because after the first pass, you would expect deformations to accumulate at different rates in these very different soils. So it's useful to calculate them separately, but it also gives us the subgrade rut, and we'll look at the advantages of that later. So how do we calculate the permanent rut on the first pass? To explain that, I'm going to go back to the plate load test that you saw earlier from the testing in Canada. So we get a load settlement curve that looks like that. So there's a closer look at the graph. Now we get to failure about here. So we don't actually need all that plateau there. Let's zoom in to that part of the curve there. So we apply a pressure and we get to failure here. So this is the failure pressure here. This is the bearing capacity of that plate. Now, if we were to unload the plate, let's say at 100, 200, and 300 kilopascals, we would come down a steeper unload-reload line, because this is just elastic deformation, and we would have a permanent settlement at each of these values. And you see how it's growing more rapidly. So the gap between these gets bigger and bigger until we get to failure. So we could actually plot these permanent settlement values against the applied plate pressure, and we would get this red line here. Similar in shape to the total one. This one includes the elastic, and the gap between these represents the elastic rebound settlement. So we're interested in this relationship between permanent settlement and applied pressure. Now, if this is the failure line here, let's normalize the results. So over here, I've got something called a mobilization factor. It is the applied stress divided by the stress at failure. So when it reaches failure, you have a value of 1. I've also normalized the settlement by the plate width. So now we have a curve that can be applied across a range of different cases with different sized plates and different strengths of subgrade. Let's just change the axes. Let's flip them over this way. This is how this sort of curve is normally presented. That could be represented very well by a hyperbolic curve. So the settlement at any mobilization ratio could be predicted using a curve such as this. So the permanent settlement depends on the mobilization of bearing capacity. And when the mobilization gets to 1, we have a mechanism. So this would become infinite, this value. But at typical values we would expect in service, we will be down here somewhere. This allows us to predict the permanent settlement of this plate for any mobilization ratio. So we derive curves like this to predict the permanent settlement under a wheel load. So let's look at that here. So let's say we're trying to predict the subgrade rut. So how much is this subgrade going to settle? Well, we calculate the bearing capacity using the t-value method. That's exactly the same method that we use for platform design that you saw earlier on. So you see the consistency between different applications. So we calculate the bearing capacity for the width of the tire. So we need to know the width of the tire and the dimensions of the contact area. Using the method you saw earlier, we can predict what pressure is needed to be applied here to make this subgrade fail. Then we calculate the actual pressure that is applied using the tire contact area method that you saw earlier. So we have pressure applied and we have bearing capacity. We calculate the ratio of the two, and that will be our mobilization factor, MT. Pressure applied divided by bearing capacity. And then we derive a hyperbolic equation that you see here with some numbers here that have been calibrated from a number of trafficking trials and plate load tests. So from this curve, once you know the MT value, you can read off the permanent settlement of the subgrade divided by the width of loading. So this is the settlement on the first pass. As I said, it's been derived from a literature review of trafficking and cyclic plate load tests. Now, Giroux-Han uses a similar approach to this, but it only has a linear relationship between the mobilization and the settlement. That's why it has a narrow field of application. You can only use it for a narrow range of rut depths. But with this curve, we can go all the way down to very small rut depths if we like. Now, we're calculating subgrade rut and aggregate deformation separately. So what about the deformation of the base layer? Well, it's a very similar approach. We calculate the bearing capacity using a normal bearing capacity calculation method, such as Tensar, for surface bearing capacity entirely within the granular layer. So we have the width of the tire. We calculate the actual pressure that's applied. If it's a dual tire, we only look at one tire at a time for the aggregate deformation. Again, we calculate the mobilization factor, and from another curve appropriate for this aggregate, we get a relationship between the mobilization and the aggregate deformation on the first pass. So we've derived this in a similar way to the other curve. Giroux-Han and other methods do not consider aggregate deformation at all. Again, for that reason, they have a narrow field of application. The Giroux-Han method should only be used for a certain ratio of CBRs. But again, people ignore that and they continue to use it for other cases. But this method works even if the subgrade CBR is very high. It will calculate all the deformation just in the granular layer. So that's how we calculate the permanent settlement on the first pass. Just a quick note about rutting, which is slightly different to the surface settlement. So the settlement at the surface and the subgrade is just the amount that it moves downwards underneath the loading. But the rut can be different when we start to get heave at the sides. It's the difference between the heave and the settlement here. So we need to do designs in terms of rut depth usually. So we need a way of converting from this, which is related to bearing capacity mobilization, and this. So we looked back at the TRL tests that Mike showed you earlier and plotted the measured rut depth against the wheel path settlement and found a very close relationship. Up to 38 millimeters, the wheel path settlement equals the rut depth because there's no heave at the sides. But once you go beyond that, you start to get this heave and you see how the rut depth increases more rapidly than the wheel path settlement. So we use these two lines to convert from the wheel path settlement to the rut depth. As I mentioned earlier, this method calculates the subgrade rut as well as the surface rut. And you might think, well, why do I need the subgrade rut? Well, you could argue that the subgrade rut is more critical than the surface rut. Yes, more serious. Why is that? Well, if you did get a surface rut, it's relatively straightforward to repair. You can just level it off. But the subgrade rut, first of all, you won't even know it's there. Secondly, if you want to repair it, it's much more difficult. You've got to remove the aggregate in order to repair the subgrade rut. Why is a subgrade rut a problem? Well, if you get some rain, it'll percolate easily through the aggregate and it will pond on top of a low permeability subgrade. And it will stay there and slowly infiltrate into the subgrade and cause it to soften and it will have a lower CBR, which means that the rutting will then accumulate even faster. So you'll get a rapid degradation of the road. So it's very good to avoid. And when you go into Tensar Plus, you will see that you have options to improve the subgrade protection level so that it keeps the subgrade rut small to avoid this problem. Now, everything so far has been rut depth on the first loading. We need to add the accumulation of rutting. So a quick look at rutting, accumulation, or deformation modes. This is a typical static or monotonic test of failure. Could be in a triaxial cell. Deviatoric stress against axial strain, you get to a failure, stress QF, following a curve like this. But imagine we did cyclic testing. There's an important stress level called the threshold stress. If we did cyclic tests, so repeating the load up and down to a stress that's well below the static failure, but above the threshold stress, you will see that the accumulation of deformation may not slow down. It may accelerate, and you get something called ratcheting deformation because it's stepping up and up and up, and it never stops and will eventually reach failure. So we want to avoid this in a road design. We want to keep the stress level below the threshold stress, because if we keep it below the threshold stress, we can do cycles, and it doesn't matter how many cycles we do, the accumulation of deformation is always slowing down. So these curves, these loops get closer and closer together, and you may reach a condition called the shakedown condition, where you get no further accumulation of deformation. So this pattern of deformation is called shakedown deformation. Let's have a look at them. Let's look at the accumulation of permanent strain plotted against number of repetitions. So these are the same curves that were shown before, but just plotted in a different way. You see how ratcheting may initially slow down its rate of accumulation, but if it's above the threshold stress, could get to failure. Shakedown means the deformation is always slowing down. Its rate of accumulation is always slowing, and it may reach a plateau when it reaches the shakedown condition. If you have a very light loading, you could have entirely elastic deformation, and you'll get no accumulation of permanent deformation. But in the case of a road design, that would be an uneconomical design. It's okay to allow some permanent deformation so that you can have a more economical and efficient design. So we want our roads to follow this shakedown pattern. So we need a way to predict shakedown deformation. There are many curves in the literature to do this. Usually they are different for cohesive or fine-grained materials and different for aggregates and coarse materials. Very few predict the actual shakedown to a plateau. We wanted to introduce a new method that covers all the soil types. So we looked back through the literature at a number of different cyclic tests on different soils. We found a curve that fitted most data quite well to a high number of load cycles. So by plotting the data in this way, by plotting the accumulated plastic strain divided by the plastic strain on the first loading, we get a dimensionless value here. So we plotted that against the number of cycles of loading, plotted as a log of the number of cycles of loading. So when n equals 1, the log of n equals 0, and this value equals 1, because on the first pass, the plastic strain equals the plastic strain on the first pass. So they all start at number 1, and then they accumulate in this pattern here, eventually reaching a plateau when they get to shakedown. So that can be represented by this curve, or this equation of this curve. It has a single input parameter, alpha. And alpha has a physical meaning. It is the distance from here to here, which is the permanent strain needed to get to the shakedown condition. And we assume that the maximum slope here occurs halfway between these 2 points. And that happens at a number of cycles equivalent to alpha raised to the power 5. Now, these assumptions have kept the equation very simple, a single input parameter. But we found that we were able to characterize the shakedown, deformation, accumulation in a whole range of soils just from one parameter. So that's represented here. So this is the same graph that you saw before, but we've plotted curves that we have derived from a range of soils, all the way from a highly plastic clay down to a sand, a road base, and a rail ballast. So what we see is that the coarser materials tend to reach shakedown earlier. You see they're reaching a plateau already here. And then with the fine-grained soils, it depends more on the plasticity. So a highly plastic clay, you see, will probably never reach shakedown, even at 1 million cycles. The line is only just starting to change direction here, just starting to flatten off. But the advantage of this characterization method is that once tested, we can design any aggregate with any geogrid on any subgrade. So we can characterize both the road-based material and the subgrade all by the same approach. And when we add geogrid to the aggregate, we can test it in our large triaxial and still derive these curves. So this is, you calculate the rut depth on the first cycle. You will use these same curves to calculate the accumulation of rut depth normalized by the rut depth on the first pass. And you can do it to a very high number of cycles. So that's how the rut depth calculation is made. I'm just going to go quickly over a few additional features of the design method. So one is wander. Everything we've looked at so far is considered channelized traffic. So it assumes that the wheel goes on the same path every time. But in reality, of course, that doesn't happen. If you watch vehicles going along an unpaved road, you will see a range of paths, but they will tend to cluster around a mean path and follow a normal distribution such as this. So we can define a wander as the full width of wheel paths that we see, and for practical purposes, that's plus or minus 3 standard deviations on a normal distribution. And by making some simple assumptions about what happens to the rut depth when wheels go on paths adjacent to the mean, so when the wheel passes along here, maybe the rut depth will actually reverse a small amount when a wheel crosses over here. We did a parametric study using the normal distribution, and we came up with a correction to the number of passes based on the wander and the tire width. So if you have a very large wander, your B over W value will be down here somewhere. So in reality, your number of channelized passes may be only about 20% the number of total wander passes. But if you have a small wander, so nearly channelized traffic, you'll be over here somewhere, and the number of passes will be almost the same as the channelized traffic. So we have this feature in Tensar Plus. You will notice that it makes a small difference to outputs. So you need a very large wander to make a significant difference to the design. That's because even if you only have 20% of the number of actual passes, the majority of the deformation happens in the first few passes. So it doesn't make a big difference, but if you do have a large one, that you will be able to make a bit more of a saving on the thickness of the aggregate. Another advantage of the method being based on bearing capacity failure is we can avoid immediate bearing capacity failure. So as well as rutting failure, you can get this type of failure just as this drives off the end of the MS cell. There you see an immediate bearing capacity failure. So that's not rut depth accumulation, that's just immediate failure. So there's automatically a check in the design. We don't let the mobilization of bearing capacity get too high. Now, another feature of the design method that is actually a completely separate calculation, because based on feedback, when the design method was being developed, we asked designers how often do they have a problem with excessive rut depths. And the answers we got were sometimes we do, but actually we have also often a problem with the waterbed effect. So if I play this video and you watch what happens when the bucket is pushed onto this road, you see the waterbed effect. This is caused when the soil beneath liquefies. So if it's a silty soil and it's saturated, and due to loading or vibratory compaction, you can cause its liquefaction. Let's see if we can play that again. You get this effect, but you notice it's elastic. It bounces back immediately. So this is not rut depth. This is a completely different phenomenon. So if you look in Tensar Plus, there is a part that will, if you have a silty subgrade and it's saturated, it will increase the thickness of the aggregate layer to keep the elastic deformation below a certain limit. And that is using an elastic deformation function that I don't have time to show you now, but I've just put this here so that you are aware that it exists. Now, everything I've shown you so far about unpaved roads does not mention GeoGrid. Just like the t-value method, we've developed a completely new design method that anybody can use, even if they're not using GeoGrid. It's a much more powerful design method than the existing methods. But of course, the reason we developed it is so that we can incorporate mechanical stabilization in an accurate way and make savings in design. So how do we introduce mechanical stabilization? Well, for every aggregate type and GeoGrid product, we do our large monotonic triaxial testing to derive the TSS model parameters. So that is the mechanical stabilization measurement. That goes into FEA models, and we run parametric studies of bearing capacity. That allows us to derive the t-value relationships that you saw earlier. We do our full-scale validation, and that gives us parameters for platform design, as well as giving us parameters for unpaved roads design that is based on bearing capacity. We also derive elastic stiffness from the triaxial testing and run more parametric studies to take account of the waterbed effect in unpaved roads. We also do cyclic triaxial testing so that we can derive those deformation accumulation curves that are used in unpaved roads to predict rut depth accumulation. So it's a long process. So to use our design methods with GeoGrid, you need to go through all these steps. And not only that, we need to do some full-scale validation of the unpaved roads design method. So that was done at the US Army Corps of Engineers test facility. You saw this truck earlier in the tire contact area study, where we did a full trial on an unpaved road with Tensar Interacts. with a 44 kilonewton dual wheel running 10,000 passes with a wander pattern on an aggregate base of 250 millimeter thickness with Interax GeoGrid on a plastic clay subgrade of 2% CBR. So we use those results to validate the design method and the input parameters. Now, I showed you some publications. There are 2 more publications undergoing peer review for the unpaved roads method, so they're not available yet. In the meantime, if you go to Tensar Plus and you go to the resources section, you can download some documents that describe what I've just been through. So here it is, the Leeds approach to applied mechanical stabilization, that's LAMS, and this is the unpaved roads method, so it describes that. So to summarize the advantages of the new unpaved roads design method, you remember we now have the tire load precision, so we can look at a wide range of vehicles, even very specifically at unusual vehicles when we have the tire dimensions. We can look at any rut depth to 5 inches, that's 125 millimeters, but very small rut depths if you want higher performance as well. So that allows you to design to pass a proof roll. So I don't know whether you ever had that requirement, but in some countries, they run a certain vehicle over a road and measure the small rut depth to check that the road has been constructed adequately. So we can even design for those small rut depths using the new approach. We predict surface and subgrade rut to improve the life of the road. We can take account of wheel wander. The approach that we've taken using fundamental soil mechanics means that we can adapt this design method for any subgrade soil and any aggregate type. So we're already looking at lower quality aggregates with Tensar Interax to construct roads from. It also takes account of elastic and resilient deformation to avoid the waterbed effect. We've got excellent industry expert and academic feedback. In fact, we've co-authored the papers with prominent academics in this field. And it all came from the fundamentals. How do we characterize the mechanically stabilized layer? So last slide, you see the new applied mechanical stabilization design methods for unpaved roads with Tensar Interax as well as platforms. We've updated the t-value method. So you too can benefit from the cost, time, and environmental savings of this new design technology, as well as the GeoGrid technology. So if you haven't looked at Tensar Plus yet, please go to tensarplus.com or use the QR code and try it out for yourself. And that brings me to the end. Thank you very much for listening. If there's time, I'd be very happy to take any questions.
Okay, Andrew, thank you very much for a comprehensive and incredibly clear presentation. I'm sure that people who are listening to this will realize that a lot of work has to be done to develop a design method. But I think what's so interesting here is how you describe about going back to the real fundamentals, doing the groundwork, and that's the starting point. So your descriptions were very clear. I have heard some of your material before, but I have to say every time I listen, I pick up a few more things, and I hope the audience today will have picked up a lot because it was so nicely presented. I think I'm just going to hand back briefly to Rifa. We'll then see where we got to with the questions. So Rifa, would you like to take over for a second?
Thank you, Pak Mike, and also Andrew Lees for your presentation. While we give time to Pak Mike and also Andrew Lees to read the questions, and if you have any questions, you can submit through the Q&A feature. And we would like to invite you to follow our social media on our Instagram at Multibangun Rekatama Patria, and we are also there in LinkedIn, Facebook, TikTok, and don't forget to visit our website at www.multibangunpatria.com, because in that website you can learn more about our products and also our projects. Now, I would like to give the floor back to Pak Mike to guide us for the Q&A session.
Thank you, Rifat. I don't know whether it's just my computer. I'm not seeing any questions in the Q&A, but maybe that's because they haven't got through to me for some reason. Is that the case?
Yes. Currently, there are no questions at the moment, Pak Mike. So if anyone have any questions, we urge you to use the Q&A feature.
I have a chance to ask a question then, if no one else has done that. So, no, actually, you did mention other material types, Andrew, and I think, I mean, a very common question we get with geogrids is, can you use them with sand? Now, I do happen to know you've been doing some testing, but what are your observations, say if you want to consider using geogrids with sand? Because it's quite common in some countries and they don't have aggregates.
Yes, it has been done. Certainly in the US, there are some cases where they have used it successfully. Of course, the devil is in the detail. There are different types of sand. Just like with the coarser materials, their performance depends on the grading and the angularity of the particles. So you would expect a dune sand, for example, not to perform very well because the particles are very fine and rounded and uniform. So we've done tests on a range of sands because we are trying to get these parameters into the design method. So we know it's been tried out and it's worked in a more empirical way, so just observing the performance, but we want to put numbers to it. We're getting close to it. We've done the triaxial testing. We've done the FEA parametric study. We're pretty close to the final stage of deriving the input parameters to the design method. So before long, you'll see those aggregates appearing in Tensar Plus, and you'll be able to actually do a design with sand. We're needing to be careful about how we characterize these materials. So we can't just say sand for the reason I just described. There are different types of sand. So we're just working out about how we make it clear what types of sand these parameters are intended for.
Yeah, okay, I think we have a question popping up. So I see, we'll see, this is from Gerald Bautista. I don't think he's Indonesian, but can we use this in base course materials? I'm assuming in that case, this is very high quality granular materials rather than other kinds of base course. But yeah, but please, I don't know what you have to say about that.
Well, the method is intended for base course materials, yes, to be used in unpaved roads. So if you go to Tensar Plus now, that is those are the aggregates that you can select at the moment, a high quality crushed rock, well graded aggregate as typical of a base course. But we will develop more aggregate types, including sand, in the near future. So you'll see those appearing in Tensar Plus.
Okay, no, thanks, Andrew. Actually, well, there isn't another question, so I'd like to ask you one more thing because I think it's related to that. I know that when we did that plate load testing in Canada, to begin with, things didn't match up very well. Your predictions were not matching very well the performance until you tested that gravel that was derived from river gravel. Yes, that was, and that then helped you to demonstrate that yes, everything works as it should do. I think I'd be interested to hear a bit more about that because I remember it happening some time ago, but I think it relates very well to the fact that you need to look at different materials with different geogrids to derive all the models for these different circumstances.
Yes, indeed. It highlighted the importance of characterizing aggregates appropriately. So just describing it in broad terms, even in the terms that often appear in specifications for highway works, those gradings tend to be across quite a wide band. And other factors are important, such as the angularity of the particles. So a crushed rock will perform much better than a crushed gravel, for example, which may be a sub-rounded type material. And then when we introduce the geogrid, sometimes those characteristics have an even bigger effect because we're looking at interlock with the geogrid. So an angular crushed rock aggregate will interlock very well with the geogrid, but something less angular, like a crushed river gravel, may not interlock quite so well. So we need to reflect that in our design methods. So that's what we're working on. We're testing all these different aggregate types because our goal is always to be more accurate and to make our designs very efficient. But as we get more and more accurate, we need to be more and more specific about what aggregates we are actually referring to. So the more traditional design methods, the more empirical ones, they had a lot of conservatism in them. We could be more relaxed about what the aggregate types were that we are talking about. But as the design methods get more precise, we need to be more precise about what materials we are referring to in our designs.
No, thank you, Andrew. I'd have to say that Gerald came back with a bit more explanation. He's actually from the Philippines. That explains a few things. But he was actually talking about ground, or I guess crushed boulders. But then he says, what is the best mixture of aggregate sizes, fine and coarse, to get the best performance for fill? So they seem to be very much related. But do you have any final comments to make for Gerald? Because we do have a couple more questions after that.
Okay. Well, the better the grading, generally, the better performing it is. So if you are going to blend materials, you need to get as good a grading as you can. There are different ways of characterizing a grading, as referred to in various specifications in different countries. So if we're talking about crushed boulders, we don't want them to get too big because it's difficult to work with large materials when you're trying to create a certain thickness of roadway. And then with our geogrid products as well, if you look at the aperture size, they are suited to particles of a certain size or a range of sizes. So we don't want them to get too big. So yeah, you can contact Tensar or Tensar distributors for more specific advice about any aggregate that you may be considering for a project.
Thanks for that. I have another question now. This is from a slightly different topic from Ispamo, who is from Multibangon. He said, thank you for the nice presentation. What is the effect of, with or without, drainage on unpaved roads on soft soils? I mean, any indication of the percentage of any effect?
Well, you need a road to be free draining. So if you're expecting a lot of rainfall, that needs to be taken into account in the design. So water that percolates through the aggregate layer needs to then be able to leave. You don't want it to sit there on top of the subgrade. That's something that I mentioned before. So to help with that, you can design to a certain subgrade protection level so that the subgrade does not become rutted and create areas for water to pond. So it's good practice to design the aggregate so that, that the grading is such that it will be free draining, so not too many fines within it. Actually, with working platforms, the same thing applies, but when you do a design, it can take into account the effect of water. So if you wanted to look at a design case where the platform was saturated with water, although that's not a desirable case, you may want to consider it. So the T-value design method does take into account the effect of water sitting in the platform. If you think that your subgrade is going to increase in moisture content, then you need to adjust the undrained shear strength appropriately, so that all effects of water on a cohesive soil come in the SU value.
No, thanks. Okay, well, one last question from Valdi, who's also from Multibangen, but he said, is there any correlation or result if the this is related to the parametric study conducted with the FEM, regardless of tire width? In other words, is tire width always a significant parameter in the results of the analysis?
It is, yes. So when we do our parametric studies, we look at a range of widths of loading. So when we do our parametric study, we don't distinguish between whether it's a tire loading or a track loading. It's just a width of loading in the analysis. Mm. So it does have a big effect, but it has a big effect relative to the thickness of the platform. So we always talk in terms of the ratio H over B.
Okay, no, thank you. Well, Andrew, I think we've come to the end of the questions, and I know we want the quiz to get underway, and you'll be excited to listen to the answers or see what people decide is the right answer for each of the questions, I'm sure. So I'd just like to thank you again for taking time out to talk to us here in Indonesia. I'd have to say I think the clarity of what you presented was really excellent today, and I'm absolutely sure participants will have learned a lot from that, and I hope it opens people's eyes to the fact that the design of these forms of structure is not something you can just kind of guess at. They can be designed properly. We can both avoid problems and save money if we design in the right way. And of course, the starting point is good parameters, good knowledge of the loading and so forth. But then the actual method of calculation is also important. And Andrew, you put that together very nicely today. So thank you one more time. So Andrew lives in Cyprus, as I mentioned, so I guess he's still quite early in the morning, but no, maybe getting on a bit in the morning there. And thank you again, and I will therefore hand back to Rifa.
Okay. Once again, thank you, Dr. Andrew Lees, for your excellent presentation, and thank you also to Bapak Mike Dobie for guiding the session. Next, we will be moving on to the fun quiz that will be led by Bapak Tri Setyoharto. Please give Pak Tri a minute to prepare for the quiz. Please note that the prize is only eligible for those who live inside Indonesia, and the quiz session will be guided in Bahasa Indonesia. To Pak Tri, the time is yours.
Oke, Selamat sore Bapak Ibu, perkenalkan nama saya Tri Setioharto yang akan memandu acara games kali ini ya Bapak Ibu. Games kali ini disampaikan dalam bahasa Indonesia Bapak Ibu, jadi nggak usah khawatir Bapak Ibu. Tapi pertanyaannya dalam bahasa Inggris ya Bapak Ibu. Jadi kalau yang tadi memperhatikan tuh Pak Andrew sampaikan, nah berhubungan dengan itu semua ya. Oke, kuis kali ini berhadiah total Rp750.000 dalam bentuk e-money ya Bapak Ibu untuk 3 orang pemenang. Pemenang pertama mendapatkan Rp300.000, pemenang kedua mendapatkan Rp250.000, dan pemenang ketiga mendapatkan Rp200.000. Hadiah hanya bisa diklaim bagi yang berdomisili di Indonesia ya. Jadi kalau yang ikut di luar negeri mohon maaf, jadi paling cuma ikut aja. Hadiahnya nggak bisa diklaim. Oke, Bapak Ibu, untuk mengikuti games kali ini, Bapak Ibu cukup membuka browser lalu masuk ke menti.com Bapak Ibu. Lewat HP bisa, lewat laptop juga bisa, lewat komputer Bapak Ibu. Masuk ke menti.com dari browser, lalu masukkan kodenya ya Bapak Ibu ya. Oke Bapak Ibu, masuk ke browser, ke menti.com, lalu masukkan kodenya, itu kodenya yang di depan layar Bapak Ibu ya. 87840880 Bapak Ibu. Nah, setelah Bapak Ibu masukkan kodenya, masukkan nama Bapak Ibu sesuai dengan nama yang diregistrasikan. Kenapa? Karena untuk memudahkan panitia jika Bapak Ibu menang tuh namanya sesuai. Jadi klaimnya benar gitu. Jangan tulis asal-asalan namanya Bapak Ibu. Oke, sambil menunggu yang peserta yang masuk, saya ulangin lagi. Bapak Ibu cukup membuka browser, lalu masuk ke menti.com, lalu masukkan kodenya, lalu masukkan nama Bapak Ibu. Untuk memenangkan games kali ini cukup mudah Bapak Ibu. Cukup jawab dengan cepat dan benar ya Bapak Ibu ya. Cepat dan benar, tapi kalau Bapak Ibu misalnya benar tapi lama, keduluan. Oke, Bapak Ibu. Oke, kita mulai ya Bapak Ibu ya. Kita mulai. Perhatikan layar Bapak Ibu. Jawab dengan cepat dan benar Bapak Ibu ya. How do we measure the mechanical stabilization of aggregates at Tensar? Nah, yang pertama tuh large direct shear test. Yang kedua large sweep cast test. Yang ketiga large triaxial test. Nah, Bapak Ibu mana tuh? Kalau tadi ngedengerin ini gampang nih jawabannya. Harus cepat dan benar ya Bapak Ibu ya. Cepat dan benar. Ini gampang nih Bapak Ibu. Yang pertama large direct shear test, yang kedua large sweep cast test atau large triaxial test. Nah, Bapak Ibu. Ayo Bapak Ibu. Yang tadi ayo pada ngapain? Oke. Jawabannya adalah nah, Bapak Ibu. Yang ketiga ya Bapak Ibu ya. Large triaxial test. Kita lihat skor perolehan sementara Bapak Ibu. Waduh, ada Bapak Antoni. Siapakah yang nomor 1? Wih, Pak Antoni emang hebring nih Bapak Antoni. Oke Pak Antoni pertahankan poinnya. Ini yang lain jangan mau kalah. Masih bisa menyusul. Kita lanjut ke pertanyaan kedua ya. Baca baik-baik dan jawab dengan cepat dan benar. What shape did we measure for the tire contact area? Nah, circular, rectangular, atau triangular? Nah, pertama, kedua, atau ketiga Bapak Ibu? Circular, rectangular, atau triangular? Ini yang nyimak nih gampang nih Bapak Ibu. Pasti tahu. Pada bengong berarti pada nggak merhatiin. Vote-nya lama. Kalau benar tapi lama nggak masuk poinnya Bapak Ibu. Itu di bawah. Harus cepat Bapak Ibu. Kalau bingung langsung tembak aja Bapak Ibu ya. Kita lihat jawaban yang benar. Nah, jawaban yang benar adalah yang kedua ya, rectangular Bapak Ibu. Kita lihat skor perolehan sementara nih Bapak Ibu. Wih, poinnya Bapak Maxwell yang tertinggi. Wah, Pak Antoni mana? Tenggelam, Pak. Oke, lanjut pertanyaan ketiga ya. Jawab dengan cepat dan benar, Bapak Ibu. What is the correct order of this deformation modes from smallest to largest permanent deformations? Nah, yang pertama, shake down ratcheting elastic. Yang kedua, ratcheting shake down elastic. Atau yang ketiga, elastic shake down ratcheting. Nah, itu urutannya mana Bapak Ibu? Yang benar ya. The correct order. Urutan yang benar yang mana Bapak Ibu? Tadi kalau ngedengerin Pak Andrew pasti tahu nih. Ya. Kalau yang nggak tahu udah tembak aja Bapak Ibu. Jawab, moga-moga bener ya Bapak Ibu ya. Ini kalau lama begini ada yang mikir pasti nih detiknya. Kalau udah vote semua biasanya langsung ini nih. Oke, mana yang benar Bapak Ibu? Urutannya. Oke, udah vote semua. Jawabannya adalah yang ketiga Bapak Ibu ya. Elastic, shake down, dan ratcheting ya Bapak Ibu. Oke Bapak Ibu. Sudah pertanyaan terakhir. Kita lihat siapa pemenang pertama, kedua, dan ketiganya Bapak Ibu. Oke, siapa yang beruntung kali ini? Wih, Bapak Maxwell. Selamat ya. Pak Maxwell JHN, Maxwell John ya. Yang kedua, Jungkook. Sama yang ketiga, Ibu Melisa. Selamat untuk para pemenang. Jangan lupa klaimnya ke panitia ya Bapak Ibu ya. Oke. Dan saya sampaikan juga ke Bapak Ibu, jangan lupa BPJS-nya. Bayar pakai jempol dan subscribe di sosial media kita. Follow sosial media kita terus untuk mengetahui acara-acara kita yang terbaru Bapak Ibu. Oke. Selanjutnya saya serahkan kembali ke Ibu Rifa.
Thank you, Patri, for guiding the quiz, and congratulations once again to all the winners. Ladies and gentlemen, we have now reached the end of the event. Before you leave this webinar, we would like to inform you that you can access your e-certificate and the soft copy material from the speakers by visiting the link linktr.ee/MRP webinar or clicking the link in the chat box. After filling out the quick survey, you will be redirected to the e-certificate. Don't forget to follow us on social media, on Instagram, LinkedIn, Facebook, and also on our YouTube channel, and visit our website at www.multibangunpatria.com for more information about our events and products. Once again, thank you for your participation. We hope we can see you at the next event. Finally, good afternoon and stay healthy, everyone. See you later.
Ya, kembali lagi. Hari ini kita bersama-sama ada di proyek Escape Plan Tol Cisumdawu. Ya, bisa dilihat ya. Nah, bangun multi-block retaining wall system.
go. I got guns in my head and they won't go. Spirits in my head and they won't go. I got guns in my head and they won't go. Spirits in my head and they won't go.
Den, kita udah nyampe mana, Den?
Ay, dari Pramuka ke Suprapto nih, sekarang Suprapto.
Masih multi-blok nih. Kenapa hormat?
Suprapto, legend.
Oh, Legend Suprapto.
Legend.
Kecil nih tapi.
Gak apa-apa. Sekalipun kecil itu ada fungsinya. Fungsinya tuh buat menahan jalanan ini. Katanya di sini perempatan Coca-Cola. Tapi gue nggak tahu, gue nggak merasakan ada Coca-Cola. Kayaknya gue mesti cabut dulu ya. Nah, ini baru ada Coca-Colanya.
Ini perempatan Coca-Cola ya.
Coca-Cola. Oke, jadi kita di tengah-tengah flyover Suprapto. Di situ ada multiblok. Di situ juga ada tuh. Ada multiblok semua. Kereta New System udah tahan lama sejak 2006. Setelah berjalan jauh, sudah dulu untuk nyari proyek MRP di edisi Suprapto. Dan sampai ketemu di nyari proyek MRP yang lain. Sekarang gue mau makan dulu. Ini dapat makan nggak sih?
Den, kali ini lu disuruh nonton di Pramuka.
Nonton di Pramuka? Bentar.
Lu ngapain, Den?
Pramuka kan katanya?
Bukan Pramuka yang ini. Tapi kita pergi ke Pramuka, ayo buruan.
Oh, ke Pramuka. Ini. Ikut. Oh, ini namanya Pramuka. 2004 sampai 2006 gitu dibangun tuh. Tuh lihat nih. Sini tuh nggak gitu gede ya, pendek ya. Tapi emang multiblok itu bisa dipakai di mana aja. Mau pendeknya segitu, mau tinggi banget, bisa semua. Oke, jadi akhirnya selesai sudah di Pramuka. Jadi sekarang kita waktunya pulang. Sampai jumpa di nyari proyek MRP yang lain.
Belum. Abis ini masih ada yang Suprapto.
Suprapto? Waduh.
I got guns in my head and they won't go. Spirits in my head and they won't go. I got guns in my head and they